Hello, I'm Norman Wobbeger, and in this lecture on linear algebra, we're going to solve the main problem in the subject, which is how to invert a change of coordinates. We're going to look at the 3 by 3 case, which is more difficult than the 2 by 2 case, which we've already done. But the advantage of the 3 by 3 case is that once you really understand it, then you can see how to generalize it to 4 by 4 and to higher dimensions. So it contains within it all the ingredients needed for the general solution. So here's the basic setup. We have 3 variables x1, x2, x3, and another 3 variables y1, y2, y3. And we are told that y1, y2, and y3 can be expressed in terms of the x's via this linear system. So y1 is a linear combination of x1, x2, x3, so is y2, so is y3. And our problem is to invert this. In other words, to solve for the x1, x2, and x3 variables in terms of the y1, y2, and y3 variables. So to get some orientation for the problem, let's recall that we've already solved this problem in the 2 by 2 case. In the 2 by 2 case, it looks like this. Here's the starting point. y1, y2 is a function of x1, x2, a linear combination of those. And then the solution which we derived had this form here. And it involved, in a very important way, this determinant, AD minus BC, obtained from the coefficients AD minus BC right there. And it was involving those coefficients in a somewhat interesting but relatively simple way. The A and the D got switched around and the B and the C got multiplied by -1. So this is what we want to generalize. It's not clear at all from this situation here how to extend it to 3 variables or to higher. But once we've done the 3 case, then we'll see what the pattern is. Now, as we'll see, the solution to this problem rests entirely on the idea of the determinant. This is why the determinant is the most important function in mathematics, as I explained to you the other day. So we have to, first of all, be clear about what is the determinant of a 3 by 3 matrix. Here are the entries of our problem expressed in a matrix. And we want to know what is the determinant of this matrix. Well, we want to think about a determinant as being an expression relating to trivectors. Okay, so if V1, V2, and V3 are the columns of this matrix, so those are 3 vectors, then we can form the wedge product between V1, V2, and V3. And I remind you that if we think of those 3 vectors as being vectors in 3-dimensional space, that represents an oriented space vector, a 3-dimensional vector in space, and we can express that trivector as a multiple of the basis trivector, where E1, E2, E3 are our standard basis. So this delta, or the determinant, is defined to be the ratio between this trivector and this trivector. That's the way we can think about what it actually is. And to compute it, here's what we do. We have a look at the 3 vectors V1, V2, V3, these 3 columns. So here's the first one, AE1 plus DE2 plus GE3. There's the second column, the third column, expressed in terms of our standard basis vectors. And let me remind you how this wedge product works, that it's linear in each one of the variables. And if any 2 of the vectors are the same, then it becomes 0. So we saw in an earlier video how to expand this out to get this multiple times E1, E2, E3. So here's the function, which is the determinant of this matrix here. It's got 6 terms, and they alternate plus and minus, and each one is a product of 3 entries of the matrix. And we noted the other day that each one of these products is obtained by taking one element from each row and each column of the matrix. A, H, F, B, F, G, and so on. And it's useful to compare this with the 2-dimensional case. In the 2-dimensional case, the same story is there would be the first column of the matrix A, B, C, D expressed as a vector. There's the second column. If we took the wedge between those 2 vectors, we get AD minus BC times the basic bivector E1 wedge E2. So that's how we got the determinant of a 2 by 2 matrix. This is how we get the determinant of the 3 by 3 matrix. And however you get this expression, there are other ways of defining it too. This is the most important number associated to the matrix, and it is the crucial ingredient in solving our basic problem. It all comes down to some beautiful symmetrical properties that this particular expression has. It may look a little bit complicated, but it's in fact very beautiful and symmetric. And we need to take a good close look at it. So I want to emphasize the importance of what we're doing now. And it's very important for you to follow every single step of the argument. So don't go quickly over this. Make sure that you check everything that I'm saying and go through each one of these expressions to make sure that I have written down the right thing. All right. So here's our matrix A. Here's the determinant of that matrix. It's got 6 terms. As I've noted before, each term has one entry from each row and each column of the matrix A. And now we're going to look at this expression in a number of different ways. First of all, what we're going to do is we're going to think of it as how it depends on the entries of the first row. Just A, B, and C. So we're going to look for the A's. There's 2 A's there, and that's all. There are 2 B's right there, that's all. And there are 2 C's right there. So we can factor it, A times this, and I'll put a minus B times this for reasons that will become clearer later, plus C times this. So I'm just expressing it as a function of A, B, and C. We see that A, B, and C first of all appear linearly, and that each of the things multiplying it are themselves like 2 by 2 determinants. What is this EI minus FH? Well, it's this E times this I minus FH. That's exactly the 2 by 2 determinant formed there. And what about DI minus FG? DI minus FG. Well, that's also a determinant. It's the determinant of the 2 by 2 matrix you would get by taking the matrix A and eliminating the row and column through B. All right. We took those things away, and then we only have the matrix DFGI, and there's its determinant. And what about the thing multiplying C here? Well, that's DH minus EG. That's the 2 by 2 determinant of that matrix. So that's quite pleasant. Is the first row special in this regard? No, it's not. It turns out that we can do the same thing for columns, and we don't need to choose the first row. We can also choose the second or the third. So these next 3 formulas are exactly the same kind of thing, but I'm going down the columns now. All right, so I'm going to take this same thing and I'm going to rewrite it by picking out A, D, and G components. Okay, so you can check that it's A times EI minus FH, and then when you take out the D's, which appear here and here, you get BI minus CH with the minus sign there, plus G times BF minus CE. So I'm concentrating on the entries of the first column. In this line here, I rewrite the same thing using the entries of this second column as primary. So B times something, E times something, H times something. And I also alternate minus plus minus for reasons that will become clear. And finally, this last row, it's C times something, F times something, I times something. And in each one of these 3 last equations, I want you to check that each one of these coefficients is a 2 by 2 determinant. And it's exactly the 2 by 2 determinant that you get by eliminating the row and column through the entry in front of it. So for example, this thing here, the F is right here. If we eliminate the row and column through F, we're left with the matrix A, B, G, H, and its determinant is A, H minus B, G. All right, so these 3 equations here, this bottom 3 that are in black, are going to be very important for us. We're going to use those to do our basic inversion problem. All right, so now we're going to solve our system. Here's the system repeated again. And I've labeled the 3 equations 1, 2, and 3. And up here I've written one of the expressions that I obtained for the determinant. The one involving A, D, and G, namely the first column of our matrix. Okay, we're going to be inspired by this formula. And what we're going to do is something exactly parallel to what we did in the 2 by 2 case. If you go back to our first video when we solved the 2 by 2 case, you'll see that we did exactly the same kind of thing. What we're going to do is we're going to take these 3 rows and we're going to take a combination of those 3 rows. And the particular combination that we're going to use is specially designed so that on the right hand side only x1 appears. The x2 terms and the x3 terms will drop out. So what we're going to do is we're going to multiply this first equation by the factor ei minus fh, which is exactly the factor appearing here. And we're going to multiply the second equation by the minus sign and bi minus ch, exactly the factor that's appearing here. And the third equation is going to be multiplied by bf minus ce, exactly this term. So we're going to do that. The left-hand side becomes ei minus fh times y1 minus bi minus ch times y2 plus bf minus ce times y3. And now what happens on the right-hand side is really cute. Okay. So what happens is the coefficient of x1, what does it become? Well, we're taking a times this minus d times this plus g times this. We've arranged it so that that's exactly delta. So the coefficient of x1 that appears is delta. So we get delta times x1. And I claim that's all that appears. There are no x2 terms and there are no x3 terms after we add them all up. In other words, if we take b times this minus e times this plus h times that, we get 0. The terms involving x2 and x3 add to 0. Now you could check that directly. You could just take b times this plus or minus e times this plus h times this and expand those 6 terms out and you'll see that they cancel in pairs and you get 0. But there's a conceptual reason why that's happening as well. It's because when we do that, when we replace A, D, and G by B, E, and H, what we're really doing is evaluating a different trivector. Instead of evaluating the trivector V1, wedge V2, wedge V3, we're replacing the V1 vector with V2. So we're replacing it and getting V2, wedge V2, wedge V3. But we know that whenever 2 vectors in a wedge are equal, the trivector is 0. So that coefficient has got to be 0. That number is going to be 0. In a similar way, when we look at the x3 term, so c times this minus f times this plus I times that, those things also combine to give 0. And the reason is either you can work it out directly, or what we're really doing is replacing the V1 with the V3. And so the trivector is V3, wedge V2, wedge V3. That has 0 area because there's duplication in the 2 vectors. Okay, that's a very important argument. Make sure, you may have to go over that a couple of times, make sure you understand what I've just said. Okay? That this particular combination of these 3 basic equations yields a new equation with only x1 on the right hand side. And so basically this solves for us x1 because now it tells us that x1 is this expression divided by delta. So we can also see why the delta becomes in the denominator because it's just the coefficient of x1 here. So that was all to find x1. Now we can do exactly the same thing to find x2 and to find x3. So let's do that. So here are our 3 equations again. And this time we're using a different formula for delta. It's the second of those 3 that were in black on that other page. And now it's expressed in terms of B, E, and H, in terms of the coefficients of the second column of x2. So motivated by this identity, we're going to now multiply the first equation by minus di minus fg, in other words that expression there. We're going to multiply the second equation by ai minus cj, and the third equation by minus AF minus CD. That will guarantee that the coefficient of x2 will be b times this with a minus sign plus e times this minus h times this. By this identity, that will be exactly delta. So on the right-hand side, we're going to get delta times x2. On the left-hand side, well, we could get minus this times y1 plus this times y2 minus this times y3. And there are no coefficients of x1 and x3, either by direct computation, you just have a look to see what the coefficient of x1 is and it's 0, or again by the same argument that we're really then evaluating a trivector, where there are going to be two v1 vectors involved. Alright, so there's x2 identified as a linear combination of y1, y2, y3. And finally, how to get x3? Well, we use the third of our identities. This one, delta expressed in terms of C, F, and I, that third column. So we use this expression now, multiply the first one by this, second one by minus this, the third one by this. There's the left-hand side. And the right-hand side, we get delta times x3. So these three equations, A1 that on the previous slide, this one A2, and this one A3, they solve our basic problem for us. Okay, it hasn't been easy, but we have now solved the problem. Let's write it down exactly what we found. So we have derived the following important theorem. Let's call it the 3x3 inversion theorem, which is concerned with inverting a system like this, involving x's and y's. And so the theorem will state that if delta, which is this combination of 6 numbers, is non-zero, then this system implies that x1 and x2 and x3 are given by these expressions involving the y1s, y2s, and y3s. There's a 1 over delta for each one of them. And otherwise, it's some combination of y1, some combination of y2, some combination of y3 added together. And those numbers that are appearing here are obtained from these numbers by forming little 2x2 determinants. This is just copying the three formulas that we've derived. This is our 3x3 inversion formula. It's a great formula, isn't it? So it's a great formula, but it's also a little bit hard to remember. So to try to make it easier to remember, let's introduce a bit of notation. If the matrix A is the matrix of coefficients of our system, then here are the coefficients of the inverse system. And we might call that matrix A inverse. So I'm just repeating now, it's 1 over delta. Here are the three entries in the first row, and then the second row and the third row. And we observe that each entry of this inverse matrix is itself, up to a sign, a plus or minus, the determinant of a 2x2 submatrix of the matrix A. And I should maybe mention that this formula for the inverse of the 3x3 was, I think, first written down by Arthur Cayley in 1858, who was a very prolific English mathematician, who was also a lawyer. All right, let's introduce a bit of notation to make this a little bit easier and to be able to say how we're getting these entries. So let's say that the minor A sub ij of the matrix A is. So I'm thinking of I and j as being indices. Remember that one way of thinking about the matrix entries is telling which row and which column it's in. So the 1, 2 entry of the matrix is the one that's in the first row and second column. That's that one there. That's the 1, 2 entry. That's the 1, 3 entry. The 2, 1 entry. The 2, 2 entry. The 2, 3 entry, and so on. So for any one of those pairs of indices, we'll have a minor. The ij minor is the matrix obtained by removing row I and column j. So for example, the A12, A sub 1, 2 would be the submatrix that you get from this matrix by removing the element in the 1, 2 position namely that one, and the row and column that contains it. So we would remove this row and this column, and that, what we left over, that's called the minor. So that would be the minor A12. So some more examples. The minor A11 obtained by removing the row and column through the 1,1 entry. So we remove that row, remove that column. We're just talking about this little 2 by 2 matrix, EFHI. And A sub 3,2, that's removing the row and column through the 3,2 entry. That's third row, second column. There's the entry H. So we have to remove that column and that row, leaving us with the matrix A, C, D, F. Okay, so there are altogether 9 such minors, 1 for every entry of the matrix. And now let me remind you that we have a number of different notations for the determinant. We're sometimes using delta of a matrix, or just determinant of a matrix, or just 2 vertical bars. All of those mean determinant of a matrix. So now let's define the adjoint of the matrix A. Okay, so this is what's really appearing in the inverse formula. In fact, there's the inverse formula there. It's 1 over the determinant of A times the adjoint of A. Okay, so what's really happening with this adjoint is we are taking minors and we're taking determinants of the minors. So we've got these determinants. And altogether, then, there's also some plus and minus signs, and they alternate. Plus, minus, plus, minus, plus, minus, plus, minus, plus. But there's one slight twist, that what appears here is not what you might think, which is the A12 minor. It's the A21 minor. Okay, what was the A21 minor? Well, the A21 minor, there's the A21 entry right there. So the A21 minor would be this matrix here, and its determinant would be Bi minus Ch. So if you look at the entry in our inverse matrix, the entry right there would be minus Bi minus Ch. So this is maybe a slightly more condensed way of writing the formula that we had for the inverse matrix. 1 over the determinant times this adjoint matrix, and the adjoint matrix itself is computed by finding a lot of 2 by 2 determinants, putting them in the right places, and adding alternating plus and minus signs. Alright, so let's have a look at some examples. Here's a matrix A, 3 by 3 matrix. Let's try to find its inverse. So the first thing we might do is calculate the determinant of the matrix. How do we do that? Well, we can memorize the formula, but it's perhaps easiest to use one of the secondary formulas that we derived in the proof of our main theorem. Namely, we can choose one of the rows or one of the columns and multiply each one of those entries by the determinant of the corresponding minor, with a plus and minus sign depending on where we are. In this case, it makes sense to choose this first column because it has a 0 in it, and so that term will be simpler because it's multiplying by 0. So how does that work? So we have to take 1 times this 2 by 2 determinant, and that's 28 minus 3, so 28 plus 3. And then we have to take minus 0 times this 2 by 2 determinant, but since it's 0, it doesn't matter what that determinant is. Plus 2 times this 2 by 2 determinant, which is minus 2 times 1, minus 3 times 4, minus 2, minus 12. So we work that out. That's 31 minus 28. That's 3. The determinant of this thing is 3. Now, to calculate the actual inverse. And I'd like to do this in some stages. So first I'm going to calculate for each of the entries the determinant of the corresponding minor. And I'm going to put that in the corresponding spot on the matrix. So let me illustrate what I mean by that. So I'm going to create a new matrix B whose ijth entry is the determinant of the ijth minor. Okay, so what would be the entry here? We have to look up here and we have to say, what's the determinant of the corresponding minor? Well, there's the corresponding minor, and its determinant, we've already seen it, is 28 minus 3, that's 31. So we put a 31 there. Let's go down. What's the corresponding determinant of the corresponding minor here? Well, we have to eliminate the column and the row through that entry. So we get that little 2 by 2 matrix there. And its determinant is minus 2 times 7 minus 3 times minus 3. We have to do a little bit of mental arithmetic here. So that's minus 14 plus 9. That's minus 5. And so we put that minus 5 right in the spot corresponding to that entry there. Okay, what about this entry here? Its corresponding minor is this 2 by 2 matrix here, whose determinant is minus 2 minus 12 is minus 14. And then we carry on. We're going to do 9 different 2 by 2 determinants, one for every minor of this matrix. So what's the corresponding determinant here? It's this matrix right here, 0 minus 2. This one here, that's that matrix consisting of the 4 corner entries, because we have to eliminate that. So 1 times 7 minus 3 times 2, that's 1. Minor corresponding to this one here is that matrix there with 1, 1, 3, 0. Its determinant is 1 minus 0 is 1. And finally, going down to our last row, the minor here is this 2 by 2. Its determinant is 0 minus 8. This one is minus 3 plus 4. That's 1. And finally, this one here has this as its minor. 4 minus 0 is 4. So every minor has a determinant, and that determinant is sitting in the corresponding position there. Now that's the majority of work. Now we just had to do one more or two more things. To find the adjoint of the matrix A, what we have to do is we have to take, first of all, the transpose of this matrix. And that means that we have to exchange each position here with the corresponding position reflected in the diagonal. In other words, we have to interchange the rows and columns of this matrix. Okay? So instead of going down 31 minus 5 minus 14, we go across. Instead of going down here, we go across. Instead of going down here, we go across. But that's not the only thing we have to do. We also have to insert plus signs and minus signs according to the position. So which positions get minus signs? These ones here. The ones where the I and the J sum up to an odd number. So that's why there's a 5 here instead of a minus 5. That's why there's a 2 instead of a minus 2. Instead of having these 1s, we have 2 minus 1s. That's the adjoint. And so the inverse matrix is the adjoint divided by the determinant. The determinant is 3. There is the inverse matrix. And that is the main computation. That is really the critical, main workhorse, difficult thing that we have to do in linear algebra. Finding the inverse of a matrix. So it's a bit of work, but it's not overwhelming. But for 4 by 4 and 5 by 5, it's a different story. Then it gets much more complicated, and we're going to have to use different techniques, which we will develop later. But this theoretical structure that we've established so far works in general. Now let's check that this matrix really has this as its inverse by doing a multiplication. Now I haven't told you how to multiply 3 by 3 matrices, but I'm going to shortly. But you can probably guess how to do it, and let me just show you what to do. So here's the matrix A. And here's the matrix A inverse, where I've brought the 1/3 out in front so it doesn't bother us. I've repeated it there. How are we going to multiply these two matrices? Well, remember what we did for 2 by 2 matrices. We started with the first column. And what we did is we multiplied that first column first by the first row, and then the second row, and then the third row of this matrix on the left. We're going to do exactly the same. So, to get the first column of the result, we're going to take this first column on the right here, and we're going to multiply it first by this row, then by this row, then by this row. And when I say multiply, it means we're going to take this times this, plus this times this, plus this times this. So a sum of 3 products. What do we get? 31 minus 4 minus 8. A little bit of mental arithmetic. So 31 minus 4 minus 24 is, that's altogether minus 28, that's 3. The next entry, 0 plus 8 minus 8, that's 0. Next entry, 62 minus 6 minus 56, that's 0. All right, okay, so next column. To get the next column, we take the second column here and multiply it by this matrix. 5 minus 2 minus 3, that's 0. Next entry, 0 plus 4 minus 1, that's 3. 10 minus 3 minus 7, that's 0. And now the last column, we get that by taking this last column here and multiplying it by each of the rows. Minus 14 plus 2 plus 12, that's 0. Next, 0 minus 4 plus 4, that's 0. Minus 28 plus 3 plus 28 is plus 3. And when we divide everything by 1/3, we get the matrix with all zeros and ones along the diagonal. That's the identity matrix in the 3x3 case. So that computation verifies, checks, that we really have got the matrix that when you multiply it by A, you get the identity. And if you like, you can check the other multiplication too. That if you do these in the opposite order, you're still going to get the identity matrix. So let's have a look at a nice example where we have y1 is x2 plus x3, y2 is x1 plus x3, and y3 is x1 plus x2. Okay, so this is easy enough that you could say, well, let's just use high school algebra to solve for the x's in terms of the y's. And you can do that very easily. Call the equations 1, 2, and 3. And then here I've taken the difference between equation 1 and 2. So y1 minus y2 equals x2 minus x1, and the x3's drop out. Now it's relatively simple to calculate x1 and x2 from these, because if we add these two equations, we get 2x2 on this side, and on this side we get y1 minus y2 plus y3. So we divide by 2 and we get this. If we take the difference, we take this equation minus this equation, then we get y3 minus y1 plus y2, there, equals this minus this is 2x1, the x2's drop out, and so x1 is 1/2 of this. And once we have x1 and x2, we can find x3 by going back to one of the original equations. Say this one here. We take this equation, we know x2, it's equal to this, and so we just bring that x2 to the other side with a minus x2. So if you take y1 minus this, and look at what it is, then you get this. That's x3. So let's solve the problem using high school arithmetic, and that's fine. But it's not as efficient and not as conceptual as what we're doing here. With matrices, we would set up the matrix A first. It's relatively simple, pleasant little matrix. It's a symmetric matrix. It's the same if you reflect it along the diagonal. You calculate the determinant. It's 0 times this 2 by 2 determinant, well that's 0, minus 1 times this 2 by 2 determinant, which is 0 minus 1. So minus 1 times minus 1, that's plus 1 from this term. And then plus 1 times this 2 by 2 determinant, which is 1. So 1 plus times 1. So altogether, the determinant is 2. And then we form the adjoint. Okay, and this involves a number of steps. I sort of combine them here. First, what you have to do is you have to find the determinant of each minor. Okay, so it's probably good to do that separately in the corresponding position. And then you take the transpose, you flip the rows and columns. In this case, it's not going to make any difference because this is a symmetric matrix. And then after that, you multiply these sort of odd positions by minus 1s. Odd position meaning that the row plus the column number is odd. So that's the adjoint, and then the inverse is 1/2 times that adjoint. And we see that this is the same as this because this first line here corresponds to this one, second line to this one, and third line to this one. So now let's have a look at the matrix operations for 3x3 matrices. These are completely analogous to the 2 by 2 ones that we've already studied. So here's a 3 by 3 matrix times a column vector. That's the first thing that we defined. And it's defined in exactly the same way. The result is another column vector, and the entries, there are 3 of them, are obtained by multiplying this column by each row of the matrix. A times x plus b times y plus c times z. Then d times x plus e times y plus f times z. And then g times x plus h times y plus I times z. And our notation is this is a matrix A, that's a vector V, that's another vector, say V prime. A times V equals V prime. And now we're going to introduce the product of 2 matrices, which essentially uses this inside it. Okay, it's a little bit complicated because they're bigger matrices. So here's the matrix A. And this time I'm not going to use A, B, C, and so on. I'm going to use the indices notation. A11, A12, A13, A21, and so on. And here's another matrix, B, with exactly the same index notation. Here is how we define the product of A times B. And I want you to think about it in terms of columns. So to obtain the first column, which is this, this, and this, what we do is we multiply the matrix A by this first column in exactly this way. So this first column is just the matrix A times this first column. So this times this, plus this times this, plus this times this, the first entry, then this times this, plus this times this, plus this times this, that's the second entry, and then this times this, plus this times this, plus this times this, it's the third entry. The second column is obtained by taking the second column here and multiplying it by the 3 rows. Dot, 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 dot. There, there, and there. And the third column over here is obtained by taking the third column of the B matrix and multiplying it by the matrix A. This product plus this product plus this product, it's the first one, and then this, 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 second one, this, 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 third one. Now there's another way, perhaps that's also useful to think about what's happening here. Suppose we're interested in, say, this entry here, which is the entry in the second row and the third column. Second row, third column. Then this entry here is obtained by only using the second row of the matrix A and the third column of the matrix B. And it's just this row times this column, by which I mean this times this, plus this times this, plus this times this. And that holds for any entry. The entry in the ith row and jth column is just the product of the ith row of this times the jth column of that. Now that particular definition of multiplication of matrices ensures this fundamental rule, that if we start with the vector V and we multiply by the matrix A, and then we multiply by the matrix B, then that's the same as multiplying by the matrix B times A. It's an excellent exercise for you to check that, to convince yourself that that matrix multiplication we defined really makes that work. It's the same as in the 2 by 2 case. In fact, when we look at the laws for matrix multiplication, scalar multiplication, and addition, everything is very much like in the 1 by 1 and 2 by 2 cases. Scalar multiplication and addition are component-wise. We do them one slot at a time. And then the various laws that I wrote down in the previous video for the 1 by 1 and 2 by 2 arithmetic for matrices are exactly holding here. The inverse law works because we have demonstrated the theorem, the inversion theorem. Namely, that if the 3 by 3 matrix has non-zero determinant, we've exhibited the inverse matrix. We have actually found it and said, here it is. Okay? And also worth mentioning that the 3 by 3 zero matrix is of course this one here, but the 3 by 3 identity matrix is this one with 1s along the diagonal and 0s off the diagonal. And the matrix A inverse that we found in this theorem has the property that A times A inverse equals A inverse A equals the identity. And this A inverse exists only if the determinant is not equal to 0. The terminology for that is that A is invertible. So A invertible means that its determinant is not 0. You can find an inverse matrix for it. If the determinant is 0, then the matrix is not invertible. You will not be able to find an inverse matrix. There was no matrix that satisfies this property. All right, here is a very useful proposition when dealing with inverses of matrices. It says that if A and B are invertible matrices, we're restricting ourselves to the 3 by 3 case here, but the argument in fact is quite general and works for higher dimensions too, and also for the 2 by 2 case. Then so is the product AB. So the product of two invertible matrices is also invertible. And furthermore, the inverse of the product is the product of the inverses, but with a little bit of a twist. The B inverse has to come first, and then the A inverse. And here's the proof. Suppose you take the matrix AB, and you multiply it by the matrix B inverse A inverse. We're assuming A and B are invertible, so these matrices really do exist. Alright, so we have these four matrices multiplying together. The associative law holds for matrix multiplication. It's a non-trivial fact. Okay? But it holds, and it means we can dispense with the brackets. Or to put it another way, we can bracket in a different way. We can combine the B and the B inverse inside here first. We're not allowed to change the order of the matrices because that changes things. But the order of the bracketing that we do, we are allowed to change. If we multiply B times B inverse, then we get the identity matrix. And then the identity matrix times either one of these is just itself. So we just get A times A inverse. And that also is the identity matrix. So we see that this AB times this matrix is the identity. And now we do the same thing in the reverse order. This one here first and then here. The argument's exactly the same. We still get the identity. And that tells us that this matrix here has this matrix as its inverse. We can find a matrix which multiplies AB to get the identity in either direction, and that's this one here, telling us that AB is invertible and giving us this formula for the inverse. Well, we've done a lot today. Well done for following. Be assured that this is probably the most difficult or one of the most difficult lectures that we've just done now in the course. Probably a lot of things will get easier. If you understand what we did today and understand it well, then you're kind of at the top of the peak in terms of difficulty. So it's worth really understanding what we did very, very well. Let's have some exercises. Give you a chance to play with the ideas, to become familiar with things, and to practice. All right, so here's a system. There's two of them. So the first exercise, solve for x1, x2, x3. Here we have this little system, which is a kind of a triangular system. And this one here is a little bit more random. Right, so you have to solve for the x's in terms of the y's. In this exercise, I ask you to calculate an inverse of that matrix there. In fact, show that it's equal to that. And also the inverse of this matrix is equal to this one. And this is kind of an interesting case because it's the case where you have an upper triangular matrix which has ones on the diagonal. Okay? So I want you to generalize this. Suppose I put different numbers here. Instead of minus 3, 4, 5, I put some other numbers. Could you predict what the inverse matrix is going to look like? The next exercise is a famous theoretical example due to Vandermonde. This particular kind of matrix plays a special role in quite a few things. It's called a Vandermonde matrix. So it's a matrix whose entries are a squared a in 1, b squared b in 1, and c squared c in 1. And a and b and c are just some arbitrary numbers. Or you can think of them as variables if you like. And I ask you to find the determinant of A, and to in fact prove that the determinant of A is this product of three differences: A minus B, B minus C, and A minus C. And also find the adjoint of this matrix A. Exercise 8.4, let's define this particular matrix R, let's say. It's 1/3, 2, 1, 2, minus 2, 2, 1, minus 1, minus 2, 2. And to give you some practice doing matrix arithmetic, or matrix multiplication, find r squared, r cubed, r to the 4th, r to the 5th, and r to the 6th. And one of these is the inverse of r, and you have to tell me which one it is. So we've been working today with 3x3 matrices in a rather algebraic way, and some of the formulas were pretty big. To really harness the full power of what we've done, we need to be able to apply it to three-dimensional geometry. Now that, unfortunately, is a subject which many students do not have a very good intuition and experience with. So we're going to have to remedy that a little bit. We're going to talk about three-dimensional geometry next time, to get you used to thinking about that as a viable framework for asking questions and solving problems. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.